Okay, hello everyone. This is the start of a lecture series that delves into diagrammatic quantum theory. So, the whole point of this lecture series is to be an accompaniment of a book I'm reading, which is called Picturing Quantum Processes by Coeck and Kissinger, and it's a free to read book that was published by department in Oxford. And I am starting this series as something to gauge my own understanding, and another thing is to help you say other people also read this or study this. And while I'm at here, I can give my own opinions on random things that I like while I'm reading this book. So I am in no way a certified teacher or of any kind. I am just here to give my opinions as I read this, and I hope it's helpful to some people, at least as a structured guide of what I'm doing to understand this. So I will be making two, three small presentations just to make the whole thing seem a little more structured, a little more, what do you say, understandable. And so I have a 7 slide presentation over here, which I'll present now. So yeah, it's titled Quantum Process Theory. The whole point of this book is to what do you say, understand quantum theory from a different kind of lens. So, in the regular sense, we would be understanding quantum theory using Hilbert spaces, which is a what do you say, a very complex topic to begin with. So, for anyone who's entering quantum theory, you would want to be familiar with things like Hilbert spaces, with linear algebra. Very strong, you would need to be in linear algebra and tensor products and tensor spaces. So, this book tries to overhaul the whole approach and tries to help you understand it diagrammatically. So, it's very simple in the sense that it's similar to things like algorithms, the charts you draw in just your regular CS course. And I thought it was fitting to understand this because the whole point of this is to use, or even though it never explicitly mentions it, it's to use, what do you say, category theory to understand quantum processes. So I am coming to this course from a perspective key. I know quantum theory, at least somewhat. I'm familiar with it, and what I want to do is I want to get an intro course to category theory through this. So this is my what do you say, my set of skills and my set goal. So starting with the first slide, what do you say, yeah, so everything about this book is about thinking in visual terms. What do you say, over here we can see that there's one object over here, another object over here. The relationship is defined by this diagram given over here, which has all these little boxes and all these little diagrams. It's schematic basically. So what do you say, this is called a process in this type of language. And what do you say, all of these little dots over here are what connect different processes together. So the whole point of this is to make things a little more easier and visual to understand, a little more intuitive. And so the point that we need intuition is because anything quantum is just what do you say, wildly erratic, and it is highly unintuitive if you're approaching it from a classical point of view, which is why you needed such powerful and what do you say, complicated tools like complex Hilbert spaces and linear algebra, etc. So we were kind of in general, we were forced with our hand to we were forced by hand to use such methods to simulate quantum processes. Very what do you say, a very standard example of weird quantum stuff is the double slit experiment. We're expecting discrete behavior, we see clear wave like behavior. A small intro for whoever is unfamiliar. The Young's double slit experiment was basically a confirmation to check if light actually behaved as a particle. And what we saw is that instead of light just going through over here, let me see if I can draw. Can I? Yeah, okay. Instead of light just going through here and passing through this little hole and just, what do you say, going straight line, mein. And what we expected is that if light is a particle, whatever was over here will go over here and straight go out like that. And whatever hits the wall just reflects back. Right? And that ended up not happening. Instead, we started seeing regions of, what do you say, where the concentration of wherever detection was strongest, and you had little dips over here where it was the weakest. So all of this led to, this is like basically the whole Armageddon of classical physics that launched a huge, what do you say, movement into understanding why this happened, and quantum theory was born. I don't know why I said birth. So with that out of the way, I will explain a typical example of why we care about this approach. So over here, what do you say? As I said, we depend quite a bit on linear algebra, Hilbert spaces, etc., tensor spaces as well. So matrices are very, what do you say, frequent visitors of our theory, and we can never actually just you say look at a matrix and intuitively tell what it's trying to do. So an example of this which I saw in the book was basically if you have, say, an image, right? So an image is easy for us to interpret visually. Like say I had a picture of here, let me just take my mouse pad. So, oh, what happened here? God. Let me fix that. Yeah, there we go. So let's just look at this image over here. This is a much easy to understand visual representation of whatever picture I'm holding. However, each of these pixels over here contain a little, what do you say, a value for like just, I don't remember what it's called, but each color is represented by a value. And if we use that hexadecimal value and we had a string of a huge series or an array of hexadecimal values just lined up all next to each other, it would be very hard to interpret that as an image of whatever this is. So over here, you wouldn't be able to read Namma Bangalore, New Valley, none of that you wouldn't be able to read. Instead, all you would see is hexadecimals, and those were very hard to interpret, right? Obviously. So that's the whole point of making this visual, is that something like a gate like this would be very hard to interpret if you just had the gate to look at. But instead, if you say had a diagram like this, then it becomes much clearer what exactly this whole thing is trying to do. So over here you can just say it's the A gate that's acting on the B gate. So that's much more simpler to understand visually compared to in the form of just this matrix. So that's what the whole book is about. We're using a very visual approach, and the whole thing is not really to understand quantum mechanics but quantum theory. So that is different in the sense that in quantum mechanics we're not worrying, we're caring about things like Schrodinger's wave equation and solving such kind of equations which require the tools given by infinite dimensional Hilbert spaces. So since infinite dimensions is kind of hard to visualize in a diagrammatic approach, we sort of avoid that and we go into a completely different we start to explore what else can we describe using just these diagrams. So if you think of matrices as a certain method of describing what you have, then picturing quantum mechanics, or the book which describes diagrammatic quantum theory, is another approach to visualize the phenomena you're seeing. So it is also another cool thing about this, I think, is that it is not just like pretty pictures and just just something that you illustrate and makes you feel nice. It is completely rigorous. It is completely theory proof. You can just it is a very valid way to present proofs, which I like. I like new methods in general. I like counterintuitive things. So this completely appeals to me because I'm a very visual person. If I hear things, I don't understand them at all. So this is a very this is something like a sign to me, man, this is calling to me. I like this. And yes, over here, as it's stated, the whole point is to make it intuitive. And now let me explain what the book is going to actually teach. So mind you, this is all just 5 minutes of just a very basic intro to the book. You will become fluent in a new language for quantum theory. You will understand a native language for quantum theory and quantum information. So again, over here it's specified quantum theory because there are things that we're paying attention to and things we're not. What we're trying to do is we're trying to capture quantum weirdness, and we're trying to represent quantum like any quantum process as a very visual and understandable diagram. So things like Schrodinger's wave equation and so on, potential wells and stuff like that are kind of hard to describe just visually, and so we try to do our best so that we get, what do you say, we get a visual understanding of what's going on, rather than focusing on, say, what do you say, rather than focusing on the details of what value each hexadecimal pixel is. We're focusing on trying to develop an intuition for some of the more obvious phenomenon. Things like quantum teleportation and entanglement are some sort of like, free gifts that these diagrammatic approaches give. Instead of having to, what do you say, rustle through the hard work of, say, 1 or 2 years and trying your best to understand quantum mechanics, instead this gives it to you quite directly, like how multiplication and addition is just given directly as a result of just counting. So counting in just regular logic, ZF logic. So yes, we prove protocols like teleportation using just simple diagrams. No prior oh yeah, so another thing about this course, or like the book that I'm going to be overviewing with you all, is key. There is no prerequisites whatsoever. Everything is given from the basic. And yeah, so this is the main idea. This is the most simplest ground basic unit that you can learn about how that you can start to understand with. Okay, so a rigorous definition: a process is anything that takes an input and gives you an output. Okay, so in some sense, it's like a transformation on a general class of objects. So, what do you say? Oh, here you have an input that is just a toaster containing bread, and your output is toasted bread. So this in the middle is the act of toasting said bread. So toasting is the process. Okay, simple example, right? In another example is, you could say ki, what do you say? You want to get from point A to B. You move from point A to B. The act of moving or the act of transportation is another process. So anything you can think of is a process. The act of writing code and getting something as an output. The act of cooking something and getting food as an output. These are all very basic examples that you can help to understand. And the main thing you should pay attention to, because these are all very obvious examples, what you want to pay attention to is how over here we have a diagrammatic thing over here. We pay attention to our diagrams. So you have object over here. We have an arrow pointing into which transformation is undergoing. F over here represents that transformation, and we have an output, toasted bread. All right, object number B, object B and object A. So with that out of the way, I will now start reading the PDF with you guys so that it makes more sense, because it's much better given than this last minute presentation I've put up, and it is a very thoughtful book, a very thought-provoking book, and so I will continue over there. Okay, hello. So now we're back, and this time we're going to be starting with our PDF. So, what do you say? You can find this PDF on, you can search picturing quantum processes, and if you want, I'll put a little link somewhere if I upload this on YouTube, or if I just keep it inside. In any case, what do you say? We have a nice, very humorously written introduction, right? Do you say? I thought it was fun to read. None of this has any technical stuff, so I'm going to skip this because this is purely for my reference and for my guide. So, what do you say? There is this chapter, there is this chapter. If you're a person who's like taking an intro to this course and also understanding what this book is about, then you can go ahead and you can read these two chapters in your own time. I'm going to directly jump to processes diagrams. Okay, so yes, all right. Okay, let me just take a pen. And can I scroll? No, I can't scroll. Okay, then I'll just untake the pen. Okay, so I'll take off my glasses as well. Yes. So in this chapter, we actually have our first intro into explaining, into technically explaining what we're trying to do with this whole book. In this, yes, it's a practical introduction to diagrammatic reasoning, and what do you say? We will find replacements for things like Dirac notation, things that are used to bracket notation, stuff like that. And what do you say? We will also see what it means to study process theory. So process theory, like just a general, generalized definition and everything rigorously given in this chapter. And along with that, as you pointed out, rather than focusing, yes, okay, that is basically it. There's a nice cute little example called Dave the Dodo from like the first few chapters, and we will be not caring about Dave the Dodo for now. Yes, and this is what I've been talking about. This is very close. This whole approach is very close to category theory, and so though this is the reason why I was interested in this book, because I want an intro to category theory. So I am taking this as a sort of a preface, or not a preface, like just a prequel to category theory. Okay, so from processes to diagrams. So if you have a physical process, how are you going to describe it as a diagram, right? And so we have a general procedure. Okay, we have to know what our inputs are, which is, so for example, we'll start with the given example, which is just a function. F takes x and y and gives you x squared plus y squared. Okay, so a process over here is defined as anything that has you say 0 or more outputs and 0 or more inputs. I said it the other way. And for this, we'll take a tangible example, our function x squared plus y. It is a process. It is a process that takes two real numbers, x and y, as the input and produces one real number, x squared plus y, as an output. And what do you say? Yeah, so the diagrammatic representation is, we would use something called a box, just a regular box. You and me, we both know what a box is. And what do you say? We would use wires coming in and out to represent what is the output and what is the input. Okay, so for a very simple system like f of x comma y is equal to x squared plus y squared, we would have two wires coming in, which is a real number over here and a real number over here, and we would have a real number coming out. Okay, so the labels on these wires are called system types, or simply types. So a similarity the author draws is that this is similar to data types in programming. So you could say, instead of real numbers, let's say we have two ints coming in over here, and it gives you another integer out there. I should use a draw tool. Yeah. So you have, instead over here, if you wanted, you could have an int, and over here also you could have an int. Okay, so two inputs coming in, two integers going in and one integer coming out. So the, what do you say, an intuitive way to understand this, that is the same as data types. And let me just exit this so I can scroll down. Here are some other trivial examples on what a process is. So over here, our data type is a list, and then it outputs a list. What is the operation, or what is the process? It is quick sort. So we take a list, we sort it in according to either ascending or descending depending on its value, and we output a list that is sorted. That's it, simple. Similarly, you can have other physical stuff as processes. So you can have just light coming in on both sides of your little binocular. What is a process? The binocular is the process, and it gives you two outputs, which is, what do you say, it takes in light from the other side, brings it back to your eyes as two other outputs of light. Okay, so this is a physical one. Like I said, cooking a meal is also a process where you just have inputs as eggs and food, and breakfast is your output. Okay, and another example, doesn't matter, because these are all very trivial examples. This is just, yeah, it's fun to read this stuff, but that's about it. Okay, and then now we shall get into a little more theoretical approach. So, because that's what we care about eventually. Yeah, so an important thing about wires in general is that they represent data flow. What does that mean? That helps you understand what connections are made where. So this is especially important when you're trying to reduce a given diagram into another given diagram. So that this is what one of the biggest uses of diagrammatic reasoning is, because you can take an essentially very complicated quantum system, and if you know how to reduce it, if you can visually see some shortcuts that you can use, you can have the same quantum process simulated by a much simpler diagram, and gives you a much better understanding of what's going on. So as we've just seen, we can put together different very simple processes to make an overarching bigger process. So what happens over here, we have, say, f G and H as our different processes, right? So H has input A and D. That same input, H has an input A and has an output D. That same output D is now inputted into a greater function, into a greater process G. Similarly, along with D, another function F over here, another process F, takes an input A and outputs another data type A. And both this D and this A are fed into G as input when you get B, C as the output. Okay. Now a lot of you are going to wonder if this is even rigorous, because all we're doing is we're drawing diagrams, boxes. When does it actually get useful? So to combat this, what we ended up doing is we ended up defining a notation. So before we do a notation, we have to have an idea of what kind of restrictions do we have with this kind of a system. Can we connect any two given data types together? Obviously not. So this is just a technical caveat. All right. So if you have an input B and an input D and an output A and an output C, and you had another box that has an input A and an output D, right? So you can only connect D to D and you can only connect A to A. You cannot connect C to either of these, and similarly you cannot connect B to any of these, right? So that is all that's explained in this page, right? That over here we have this little example over here, key A is not equal to C, because over here the corresponding output over here is C, and what we require from H is A. So we cannot have that side and this side be the same in some sense. Alright? And this helps us avoid some very obvious errors. And yeah, more complicated example is given over here with a plug strip adapter and a power drill. If you have, say, 3 different kinds of power plugs, let me show you one if I can. Or no, wait, that's a bad idea, because I'd be breaking the extension board, and it's not really required because it's a pretty simple example. You have a plug strip over here, it has 3 extra pins over here, 3 extra plugs, and it has 1 plug as input, because you have to connect your adapter. Supposing this is the adapter, you have to connect this to an electrical output, and it's going to have 3 different sockets. Those 3 different sockets are what's on the top over here. So top has output always, bottom has input always. Alright, and similarly you have one adapter over here and just a utility or just a device. And so here in this example, the point of this example is to illustrate what a type is. So in this example, UK plug is one certain type of plug, and European plug is another type of plug. So you cannot mismatch a European plug with a UK plug. And so this gives you just a better understanding of what exactly they're trying to say when you can't mix data types. Now we will go into the important thing, which is what is a process theory. So typically when we learn about quantum mechanics, what we learn the basics of a very simple case of a quantum process. So we would care about, say, the double slit experiment. We would learn about diffraction and stuff like that, and why it is better approximated by a wave function, and why light acts as a wave function. We would go on to justify that. Or another example that we can do is we can talk about, that's the only one that comes to mind right now. So in that sense, we study this one system, which is Young's double slit experiment, in as much detail as we can, and we try to justify everything. Then we take those highly advanced tools and we try to justify everything else. What this category theory approach does in this book is that it takes all of the systems into consideration at once and sees what's in common, what is different, how are they different, and how are they related to each other. So in this, we care about all kinds of quantum processes. Rather than taking one thing, studying it completely and trying to apply it to everything else, we take all of them into consideration and say, what is the general kind of process that I can study in this? And then we start to study everything else as that same general quantum process with little caveats and little special properties. So it helps you give a more general, more stronger understanding of what quantum processes do, and it helps you identify what differentiates one process from another. So this helps a lot when you're going to more exotic quantum processes. So yeah, uh, yes, let me read this out for you. Process theory tells you how to interpret the wires in the boxes in a diagram and what it means to form diagrams. That is, what it means to form wire boxes together. So a process theory is going to tell you exactly what it represents. So up over there, and this is the process theory of using a power drill. In the bottom, we see some other examples of process theory. So functions is a process theory where what do you say, where function is a process and your types are sets. So because functions are basically just, we all know the definition. A function is something that maps one set to another. So if you basically you take a function and its input is a set and its output is a set. So in the same sense, if you draw a box, your input is a set, which is why that's a type, that's a system type. Your system type over here is a set. Your system type is also a set because it outputs a set. Similarly, relations are pretty much the same as functions, it's just more looser than functions are. And linear maps takes do you say vector spaces to vector space, or like vector spaces to Hilbert spaces, or vice versa, etc. And classical processes are things, just regular classical systems like an oscillating spring. And quantum processes are things like superposition particles. I'm not well versed enough to talk about quantum processes at all. In fact, my only expertise is coming from a math perspective. So the only reason I care about this book is because I want an easy intro to category theory in a practical way. So yes, we would refer to process theory by saying what processes are, leaving the types implicit. This is a good practice because the processes are an important part. Yes. For instance, we'll see that theory of functions is quite different from that of relations, and it will not do just to call both sets. What he's talking about over here is that, what do you say, if we only care if we only care about processes individually, he's basically using the fact that we're looking at all different types of systems to justify that we can tell a certain class of systems from another class of systems. So he's basically saying that if you look at all functions at the same time and you look at all relations at the same time, you can tell the difference between a function and a relation pretty easily. Much better than you would if you looked at a particular function and a particular relation and you try to tell the difference between both. So, yes. Okay, let me explain this part. So a process theory tells you how to interpret diagrams as processes. It crucially tells when two diagrams are representing the same process. So this is what I was talking about in the intro. When you have two different, when you have a certain overcomplicated diagram, knowing how to reduce it into a simpler form is what's the strength of using using this diagrammatic approach to quantum processes. And oftentimes it helps reduce a very complicated quantum system into something much simpler and much more understandable and intuitive. So an example for this is that we can have a simple process theory called computer programs. So instead of taking instead of trying to understand, this is again a different approach to understanding programming itself. So instead of trying to understand like hello world and like print ln and stuff like that, you are now going to generally study a class of computer programs, and you're going to start looking about different data types. Over here, what are the types? Over here in computer programs, we know integers, booleans, lists, etc. And the processes are computer programs. That's why I drew the analogy to algorithms and processes, because it's the same thing. And then if you have a small program like quicksort, then its data types are the list that we're taking, and this is the process itself. So over here we're taking in the list in the first step, and then we're performing the process of sorting the list. And so over here, if in goes a list from this side, then out comes a sorted list from this side. Okay. And Yes, this is an example of why having this diagrammatic approach is useful. So if you had, what do you say? This is the kind of reductions that we're talking about, that we care about. So let me just use the highlighter instead. So if over here on this side you inputted a list, then in the middle over here you will get a sorted list. If you input that sorted list again, you would get the exact same sorted list. So this helps you draw the relation key. Applying quicksort more than once gives you the same effect as applying it just once. So this is especially useful because there are much more complicated systems out there that can use this kind of simplification. Okay, see this line over here, sorting a list twice has the same effect as sorting it once. So the reason why we call a process theory a theory is because it comes with loads of different kinds of equations, relations between one side and another side, where both of them are processes individually, and what do you say, these equations, this is called a process equation over here. I can't type, let's see. Yeah, I can't type as a skill. Process equations. So in a process equation, your LHS and your RHS, right hand and left hand, are both processed individually, which is why you see a diagram over here in both. And let me just rub this because I don't like it. And such a relation is called a process equation. Solving them is what we care about. Okay. Diagrammatic quantum theory gives you the tools to reason about why two processes are equivalent. Okay, and now let's just go a little down to a little more rigorous example that helps you actually understand what we're doing over here. So let's take the familiar example of taking a function f of x and y is giving you x squared plus y as output. Okay. So now we're talking about the process theory of functions. We've moved from the process theory of computers to process theory of functions. So the process of taking x squared plus y, which is this graph over here, which we don't really care about right now because it's just a nice illustration. So what we want to do is we want to break this down into simpler things, right? So if I had, basically what I'm doing to this is the same as me taking an input x over here, squaring it, and then adding it with the other input over here. Okay, so in this line you get just y. So y over here just goes up as it is and gets added to x, and x over here gets squared before it goes. Oh, this thing can zoom. What the hell? Can you unzoom? Oh no, it's zooming more. Help me. God. Reset zoom. Yeah. Okay, there you go. Thank God. Messy. Yeah. So we had x over here, and you had y over here. Your y is gonna travel up anyway and just get added over here. This is the process of adding. I can't write because I'm too lazy to use a text box. And this is the process of squaring. Okay, so x squared. Okay, this is what we're looking at. And if I wanted to show you an example of why this is kind of useful in this particular example, is key. You can tell the difference between a process that looks like, say if I wanted to switch the order. So if instead I had over here x squared in this part. Okay, that wrote great. Okay, and you had x and you had y. So in this example, oh no, wait, let me rewrite this. Hang on. Yeah, there we go. If I add the thing of x plus y now, and I shifted the order, basically the exact same processes, except this time I'm just switching the order. So you have x coming from one side, you have y coming from one side, and this time this is the input to this. So what we get over here, everyone knows, is just x squared plus y, x plus y the whole square. X plus y the whole square, right? So commutative is very well, we say, represented in terms of processes. So you can tell key when something is and isn't commutative. An example of commutative one is right over here. Let me just rub that. I don't know why I didn't just use the reset option. Yeah. So if you just crazy. Okay, there we go. So if you just negated your output once, negated it again, it's the same as not doing anything at all. Right? Let's go to more examples. Yes. Now, yes, I will try to explain some of these, okay? So, exercise 3.4, cook up some of your own process theories. For each one, ask the following questions. So, for our process theory, let's see. Let's go back to our old the examples that were given. Okay, so you have functions, relations, linear maps, classical processes, and quantum process. Okay, so here's some two examples. What if we had a, okay, no, again I'm writing when I should be typing. Okay, so again I'm drawing when I shouldn't be. This is a slow laptop. Okay, so let's take 2-3 examples. Yeah, okay. So our first one is differentiation, right? Or just let's just take a regular calculus. God help me with my own typing skills. Calculus, right? Okay, so its system types are functions, takes in one function, takes more than one function depending on what it wants, or you could say it takes a function over here and it takes the the variable over here. So over here you would have dx over here as your input, and over here you would have f of x. Alright, and gives you an output that is d of f, right? Okay, or df by dx. I'm not writing that because I cannot draw with a mouse. Okay, so that's the system type, so we've defined that. What are the processes? The process of this one example. Oh wait, over here I've not really defined this well. Let me redo that. Okay. Okay, so we want processes, right? So if differentiation is 1, oh no, I didn't mean to do that. Okay, and let's say down here integration is another. Yeah, so as I explained earlier, oh wait, I should go ahead and draw the write these again. Okay, so f of x, right? Here also f of x, not c, x. Here we have dx. Here also we have dx, right? Okay, these are our inputs, okay, and our output. Yes, output of here is integration of f of x dx, right? Not that, yeah. And over here we have df by dx as our output. Oh, that didn't write very well, did it? Yeah, let's draw it bigger. df by dx. Okay. This whole set of defining what a differentiation, what differentiation is and what integration is, this is a process theory. The individual thing, as in integration and differentiation, these are processes. Okay, and so okay, so we defined what the system types are, we defined what a process is, and now we have to define how these processes compose. So what do you say? Now let's just undo a bunch of this actually, because this got quite messy. Yeah, there you go. Okay, so now we need to tell about how integration and differentiation together interact, right? And for this, obviously, we know if we take an integral of d of f, we get the same function. So, and vice versa, if we switch the order of, if we try to differentiate the integral of f, then we get the same thing. So the process of, okay, wait, let me explain this diagrammatically. I think it'll click now. Okay, all right, yes, I know just how to make it make sense. So if you had diff over here and you had integ over here, right, and you had your two outputs and you had that same output over here because this is dx, right? So that's gonna go back same, and you checked what you got over here, it would be equal to not doing anything at all. So if you had, let's just take the outputs and write it down. If you had f over here, f of x, and if you had dx over here, then it's the same as just taking f. Okay, this is a process equation. It's a relation between two different kind of processes, and now this is something that you can understand visually. You didn't have to understand what differentiation and integration was. All you needed to know is that if you compose two of them together, you get the same function back, and now you have a process equation. So this is like a pretty good example of why we care about process theory in general and its diagrammatic applications. And yes, when should two processes be considered equal? We just answered that. Oh, I blocked it off instead. Anyways, we lost our examples. That's sad, but we move on. So yeah, there you go. Okay, so one thing to note is that we haven't been too careful to define what a diagram is. Okay, and so incoming is a rigorous definition of what a diagram is, which we will do in the next class. Bye.